Okay. Hello, everyone. So the topic of this presentation is kind of straightforward. It's about video quality and more specifically about VMAF. So what I'm going to try to do is give you some introduction, some background behind VMAF, and then motivate you a little bit behind the challenges that we are facing when we are designing VMAF and, let's say, future VMAF versions. So these are the 4 points of the presentation. The first point will be basically some historical background and some introduction to VMAF and how it works, but mostly at the higher level. Then we are going to be looking at some adoption use cases and some examples of VMAF being actually implemented by, let's say, organizations besides Netflix. Then we will be looking at a very, very interesting point, which is the challenges behind designing VMAF and, of course, other video quality models. And then at the end, we will be trying to answer the question, why is VMAF becoming more useful as time goes by? So the original, let's say, justification behind developing VMAF was the observation that existing video quality metrics or image quality metrics like PSNR, they don't correlate as much with subjective quality. And to very quickly get a feeling of that, here you can see 2 frames from 2 different contents, one on the left and one on the right. And you can see that humans would rate the frame on the left with a value of 19, whereas the frame on the right with a value of 69. So even though there's a big difference in the subjective rating, if we were to calculate PSNR at the scaled resolution, we would find that the PSNR values are close enough, actually really, really close, which kind of gives us a hint into the need for needing a better quality metric. And actually, this brought about the development of VMAF, which basically tries to more accurately measure human perception of video quality. And it has a number of good properties. The first one is that it is consistent across content types, which basically allows you to apply it on cartoon, apply it on natural video content, let's say in a fair and in a consistent fashion. And also it works quite well for picture artifacts that are relevant to adaptive streaming, which would be compression and scaling artifacts. Last but not least, VMAF is an open source project, so everyone is actually invited to participate and contribute to the ongoing VMAF development. And by the way, the acronym stands for Video Multi-Method Assessment Fusion. And in a little bit, we are gonna, get a hint where that term stems from. Here is a, very high-level diagram of the VMAF chronicle, basically how VMAF has evolved over time. I don't want to go into too many details of each one of these events, but basically you can see that it's a multi-year effort that has actually progressed a lot with the help of a number of universities like USC, University of Nantes, UT Austin, and others. And about 2016, the VMAF project went live on GitHub, which actually gave a lot of room for improvement from outside developers. And as time goes by, new features are being added, like libVMAF, which is basically the ability to extract VMAF scores through FFmpeg, through an FFmpeg filter. And later on, newer models were being added and some speed optimizations as well. So let's say we are kind of on the far right of that diagram, and we, of course, hope to keep extending VMAF with more and more features. The easiest way that I like to think VMAF about is that it has two different components. The first one is feature extraction, which you can see on the top of that slide. And what these features are basically trying to do is they are trying to model low-level properties of the human visual system. And we actually call these elementary features. Some earlier presentations already mentioned about them, which would be VIF, VIF, calculated at different scales due to the multi-scale nature of the human visual system, ADM, and of course, a motion feature for the temporal aspect. One of the most important properties that VMAF tries to capture is what is well known in the literature as contrast masking, which can be easily understood by basically thinking of two different types of regions, very smooth regions and very textured regions. So if we were to look at, let's say, the distortions on top of these regions, we would actually find out that if you have a highly textured region, pretty much a place where there's a lot of variance, lots of different orientations, lots of frequencies, lots of frequency content, the distortions would not be as evident as in a smoother area. And basically, contrast masking is, let's say, at the core of what the VMAF features are trying to model and capture. The second main component is the, let's say, machine learning component, which basically takes these features and tries to align them with subjective scores. And the way to do that is, of course, by training a model, gathering subjective data, training a model, which will hopefully give you a better performance, better correlation compared to using just each one of these elementary features by themselves. The way you can do that is, of course, by intense subjective experiments, where basically we ask people to come to, and we ask human participants to come to the lab. We pre-design a set of conditions, a set of video distortions, and we ask humans to rate them, let's say, ranging from very bad quality or from bad quality all the way up to excellent. And that's typically called as the ACR scale, but you can think of it as any subjective scale. Then the important step in VMAF is to actually take the scores that we have gathered, so take that subjective scale and translate it, transform it into the VMAF scale, which is from 0 to 100, with 0 being worst quality and 100 being, let's say, best quality. And you can see an example of that on the right, where basically the x-axis is the true score, the values that we have collected during the subjective experiment for a given reference and distorted video pair, and the y-axis is the corresponding VMAF score that we would get. And you can see how the axis now becomes from the ACR scale to the 0 to 100 scale. With that, I have a demo. I really hope it works. It did at home, but okay. So try to not look at the names of the videos. Maybe I'll hide it. So we're gonna watch 2 videos, one after the other, and let's make a quick subjective study and see what people think. Please don't look at the title. I'm gonna be scaling up, so this is going to be full screen, and there will be audio, just so you know.
Place is about permanence and change. So many things about Mexico abide, and I'll speak of them as lovingly as I can. From the fruit.
Okay, that's the first one. And I'll try and play it really quick so that memory doesn't kick in. That's the second one. Okay. So which one do you think is better? So the subjective experiment worked. As you could clearly see, the first video was much worse than the second one. Of course, the perception of quality changes with respect to what's your viewing distance and also what's the angular viewing distance. But actually, if you were to calculate PSNR on the scale resolution, you would see that both videos have same PSNR of 36, whereas VMAF, for the first video, it's a 67, and for the second one, it's a 76. Basically, that's a good sign because we maintain the monotonicity with the subjective experiment we just did. I'm so happy that worked. So with that, let's actually proceed to some examples, just a few examples of how industry and the academic community have already started integrating VMAF, and that will also give us an idea of some use cases that other people have actually used VMAF for. Of course, VMAF has been integrated in a number of third-party tools, notably FFmpeg, where you can basically calculate VMAF as an FFmpeg filter. in some X265 tools, in the video clarity analysis system, in the MSU video quality tool, and in the LCard analyzer. But these are just some examples of third-party tools. A very interesting use case for VMAF is actually for codec comparisons. And you can see here an example from a recent JVET meeting. And on the left, you can see a graph where on the x-axis, we have the bitrate, and on the y-axis, we have subjective opinion score. And here is a comparison between HEVC and VVC. So the authors of that work basically developed a subjective experiment to compare between these two, and they also reported objective metrics. So on the right, you can see a 2D table where basically the rows are different resolutions and the columns are different metrics and correspondingly different BD rates that you get by using each one of these metrics. So you have PSNR, VMAF, objective metrics, and last column is MOS, so the actual subjective ratings. And you can see here in this example that if you were to use PSNR instead of VMAF to calculate your BD rates, you would be, let's say, underestimating or overestimating, depending on what you're measuring, the BD rates by about 4 to 5%. Because basically, what we do have in practice is the objective metrics. What we don't have is the BD rate MOS. Thankfully, VMAF has also been used quite a bit in research papers. I just wanted, to give you a quick, a quick spotlight of some interesting papers I found, where basically VMAF is not only used for, let's say, pure video quality on adaptive streaming. So, except maybe the first work. So the first research paper is about reproducing VMAF on a number of data sets. The second work is actually a pretty interesting one, where VMAF was used on 360 VR contents. There has also been work on using VMAF for web RTC applications. And another recent line of work is how you can basically use VMAF as a ground truth to train a no-reference metric for a gaming application. So you can see how VMAF has slowly started, let's say, expanding to other very, very interesting applications, and with good results. Now, so far I've kind of said the good things about VMAF. Let's delve a little bit deeper into challenges behind designing VMAF and things that we should be keeping in mind. So the two main things I'll be talking about is the design dimensionality, and the second one, which is actually kind of correlated with the first one, is how do we deal with the presence of noise in the source and in the encode. So the first challenge, which is one of the things that keeps me up at night, is basically you have designed VMAF, let's say, for a set of specific use cases, but how can you generalize to a whole bunch of other dimensions that are out there? So let's get a quick feeling of what these dimensions are. The first one, which is seemingly the easiest one, is the fact that you have different encoders. So as you know, VMAF has been trained on an H.264 dataset, but it can, of course, be used to other codecs, HEVC, VP9, AV1, and so on and so forth. Now, even though these encoders have many similarities in their, let's say, in the artifacts they produce, they also have some differences. So, there are cases where we basically wonder, okay, why, let's say, for this specific use case, we see a different VMAF value than the one we expect. So the different encoders is one dimension. Another dimension is whether you have SDR versus HDR content. And you can imagine, of course, whenever you design a VMAF model for SDR, what happens when you develop an HDR model? Is it going to be the same model? Are you going to be doing another subjective experiment? All of these questions need to be answered thoroughly. But even within SDR content, you will have sensitivity perhaps on the brightness of the content. So if you have a very, very dark scene versus a very, very bright scene, also there the performance could change. And that's something to keep in mind when designing the metric. Yet another dimension to keep in mind is the fact that we have different viewing conditions and actually different viewing expectations. You can think the example of sitting comfortably in a living room with a massive 4K TV or even 8K these days, compared to a small device like a smartphone where you have, let's say, a 1080p screen. And all of these actually dimensions, they are pretty significant, and they can affect the predicted VMAF score. And now the key question here, the key challenge, delineated in the bottom, is how we can design a model that is both extensible, meaning that we can cover these dimensions in a sufficient manner, but at the same time consistent. In other words, whenever we say we have a VMAF of 60, we want that meaning to be consistent throughout these dimensions, to the extent, of course, that this is possible and is a fair comparison to make. The second challenge, which you can also think of it as yet another dimension to take into account, is how VMAF is going to be dealing with the presence of noise. The first example is what happens when the source is noisy for some reason. It could be an older source. It could be a source that the noise that has been added due to creative intent. It doesn't matter. And we have actually found some use cases where VMAF is going to underpredict subjective quality due to the presence of noise in the source. The second point, let's say, related to noise is how we can truthfully and in a fair way assess film grain synthesis tools like the ones in AV1. So on the bottom, I have drafted a very, very quick diagram, a simplified diagram, as a reminder of basically having a source, getting that source to estimate some noise parameter, some noise model, and then using that noise model at the decoder side to add back the noise. And these tools have been shown to improve subjective quality. So can VMAF actually capture them? And if so, how we can do, let's say, codec comparisons across different codecs, where some of them have the film grain synthesis tool on, some don't, and depending on the synthesis tools that are available. So that's yet another challenge we have to keep in mind. Now, one of my favorite questions is, why is VMAF becoming more useful? And I would say here that as new codecs are being developed and coming up, for example, AV1, AV2, and all of these new tools that are being added to the arsenal of these encoders, it is very, very important to be able to truthfully compare between these codecs. And of course, we have found a number of occasions where PSNR is not enough to evaluate them. So as long as codec development is ongoing, we need to be, let's say, supporting the codec research by supplying good and consistent VMAF measurements. Another aspect that is important is that VMAF is an open source and well-adopted project so far, which actually makes it easier to find problems. So let's say we roll out a new version of VMAF and we have not covered a specific use case, then it is relatively easy, I hope, for other people to let us know about it, or even they themselves, they can suggest a solution to improve on the latest VMAF model. And of course, the fact that we are committed to further improving VMAF as a tool generally, the documentation, resources, and the accuracy and the speed of the algorithm make VMAF more useful, because we are actively, it's a project we are working on actively. To sum up, we started off by getting some intuition behind why VMAF was developed originally, and we discussed the fact that VMAF basically tries to fill the gap in existing perceptual video quality metrics. We also saw some examples where VMAF was adopted by industry and the academic community, and also some challenges associated with VMAF, where, of course, is you can see where the room for improvement actually is. And we also saw we saw some ideas behind why VMAF is becoming more relevant, and especially I would say for new codecs, for codec comparison, being able to optimize an encoder across the entire stack And I'll also give an example about that, is how VMAF becomes more relevant. And about that encoding optimization point, in my head, there are multiple examples that VMAF or some other quality model could be used. So you can start from within one frame. You could do encoding optimization within the same shot, across multiple shots, for example, using dynamic optimizer. So you can see basically how quality and compression are really, really coupled together. And we hope that VMAF is filling this gap. That's all for today. And if you have any questions, I'm here. Thank you.
So I was wondering whether what you thought what you might think would be the influence of particular kinds of salience to human vision. I'm thinking particularly in video conferencing, we have two basic types of content. We have human faces, and we also have screen content and graphics and text. And one thing that we find is that there's a huge difference between text you can read and text that you can't read, or that is rendered difficult to read. Do you have a view on how you could improve for those situations where maybe there's a very focused human reaction to those kinds of artifacts and that kind of content?
Yep. So let me rephrase the question to see if I got it right. Basically, you're thinking something in lines of combining, let's say, a VMAF map with saliency measurements, something like that?
Yes, and also whether there's a dimension of particular kinds of content in influencing that. So if your video is dominated by human faces, you might find that your VMAF scores are less accurate than general video content, for example. If it's dominated by text, do you find those kinds of results in your testing, that the very specific kinds of content, your accuracy is lower?
I see. So let me answer that in two ways. There are some, let's say, failure cases for VMAF. And by the way, whoever finds any of these examples, they are very welcome to upload them on the GitHub repository. We have a link where people can upload examples where they have found failure. Some examples that I have seen VMAF to be failing is, let's say, if you have very, very high motion, and that could be because the temporal feature is not as sophisticated as it could be, and also the fact that sometimes in the training set, if you don't have very high motion sequences, that might affect how the SVM is doing the mapping. And I've also seen some cases where there is a lot of text, where the VMAF calculations might be thrown off, especially because when you have a lot of text, let's say the sharp edges will be thrown off right away, even if the rest of the content looks reasonably well.
Yeah. So we also find there are cases where you get sub 30 dB PSNR, and although the VMAF score is higher, they can look visually lossless, and in fact they can look perfect, but the score is still not perfect. So there are those kind of situations as well.
Yes, there can be. I would say if you have very, very extreme edges on top of natural content, like lots of text, that could be one thing to keep in mind. Regarding saliency, I would say that I believe a lot in saliency, especially if you have scenes with faces. That's basically where people are looking at. But I have not seen yet some work, maybe I'm outdated, I don't know, but I have not seen some work where a very good saliency model and, let's say, a good video or image quality metric, they have been combined and they have significantly improved performance. I've seen works where these two things have been combined, but they are usually on a few data sets. So I wouldn't say that we are not there yet, but I do believe in incorporating, let's say, higher level context into the frame level video quality maps.
So other than video compression, do you think VMAF can be extended to other like modalities such as video super resolution?
Oh, definitely. So actually, Lee Heng earlier, he presented his work where he was showing how you can optimize a neural network for compression with the proxy quality network. You could actually you could take out that deep compression module and put in a super resolution module. You could put in a denoising module. That's the first thing that came to my mind. So it can definitely be used.
A few comments. So the first comment is, sure, if we have like 20% VMAF difference, it's easy to say A is better than B. But if you notice some presentation, they're talking about 1% or 0.5%.
Yep.
How reliable do you think VMAF numbers are when you're talking about those small percentage points, which is what we're dealing right now with, extending codecs? We're comparing tool A versus tool B, like in MPEG, if you're familiar, like they're even talking about 0.1 or 0.5%, very tiny numbers. Do you think VMAF is good at discriminating, like at those small numbers, or are there instability issues? Okay.
That's a very good question. I would say that the performance, the accuracy of the algorithm changes along the quality range. And let's say that's a byproduct of the fact that you have training, and that training is not infinite. So you don't have an infinite number of samples, to cover the entire quality range as sufficiently as you would want. And a general comment is I would always report confidence intervals, no matter if it is VMAF, no matter if it is PSNR, and this confidence interval should be also on the BD rates and basically on everything that is being reported. Now, if you ask me if a 98 versus a 99 make a difference, I would say that at that very, very high range, it's probably something I would consider very similar. But there is actually a VMAF model which allows you to create confidence intervals. So if you look at the confidence intervals, I'm pretty sure there's going to be.
Actually, that's great that I hear that, because I've never seen anybody presenting the confidence intervals, but I think that's very valuable, and I think maybe that should be encouraged. Okay, because as you said, that provides you with some additional information that you should not be ignoring, especially when you're doing this A versus B, let's say selection. And another comment, even though VMAF is quite useful, let's say, in evaluating overall quality, I'm always concerned with the fact that unlike PSNR, where you have some kind of a notion of what's happening, in terms of pixels and difference and so on, up to some extent, because VMAF combines multiple different, let's say, dimensions, you lose that kind of concept when you get the number. So you don't know exactly what was, let's say, the influence. Was it a temporal aspect? Was it the spatial aspect? And so on. So I'm just wondering if you have considered, when you're generating those statistics, when you're generating a VMAF number plus, like the confidence interval, if you can also generate, additional sub numbers that talk to you about that this is the temporal impact on VMAF, or this is the spatial impact on VMAF, because at least as, let's say, codec engineers, as algorithm engineers, I believe that kind of information can influence our decisions of how we are designing a codec or how we're evaluating, a particular algorithm, because it tells us information of what might be the problem when two schemes are different. I don't know if you understand what I mean, yes. But yeah, I think at least personally for me, yes, it does tell me one number that there is something wrong or something good and so on, but I want to know what is good or wrong when I go back on the drawing table and go and fix, whatever algorithm I'm working on. And I think quite often we don't do that. We just look at the number and just report it and ignore, the actual impact. Anyway, just my own opinion. So I don't know what.
Yeah. Should I quickly address that?
Last question.
Oh.
Has VMAF been extensively tested with gaming content, more specifically like PC gaming kind of content? Does it require more training, or how does it correlate to perceptual quality?
Yeah. So good question. I have not myself tested VMAF on gaming content, but I've actually talked to the authors of these works where they evaluate VMAF or use VMAF. They have found that it works generally quite well. They have found some outliers for which they actually have tried, to play around with other features, but still, let's say, stick with the training testing VMAF framework. But I would say generally that the performance is quite well.
I can add to that as well, since I work for Twitch. We do objective analysis, and in general, VMAF is pretty good. It gives us very high confidence, and when we do subjective, it pretty much matches the expectation. So,
okay, thank you very much.
Thank you.